Okay, so a few things to announce. The portfolio course next week we're gonna have a midterm, right? So this weekend, before this weekend, I will post some questions, okay, for you to practice. But these questions are based on the end chapter questions, okay, end of chapter questions of the textbook. Okay, so basically, maybe I will post 5 or 6 questions, okay, so that you can practice. Basically, these questions will be in your midterm exam, okay. So you don't have to spend so much time generating the solutions to these questions, okay. So this is about the end chapter question, but another set of questions is about the codings, okay. Codings, so basically codings is the questions we have covered in class, okay. So I like you to become more familiar with the efficient frontier, how to generate the points of the efficient frontiers and the MVPs. So something like that. Okay, so it's not that difficult. But maybe I will give you some. I will require you to download the data from Yahoo Finance. Okay, for example, it's very simple. It's very simple. Okay, so don't worry too much about this. Okay, but maybe that's gonna take you some time. Okay, so I will give you longer times to complete the midterm. Okay, midterm exam. Okay, any other questions about the midterm? Have any questions? No. Okay. Uh, for the codings, I like you to use some AI tools to help you to generate codings, because nowadays you should become more and more familiar with AI. Okay, so especially for codings, because I don't need you to become an expert or very proficient in codings, because you don't have so much time writing codings. Okay, so if possible, you can ask AI to help you to generate codings for you. Okay, so this is one thing. Another thing is that next week for this course next week, I'm planning to give you lecture as well. That means I'm gonna defer the midterm of this course 1 week later. Okay, so that means next week. The reason is that the uh, 2 weeks later, I will not be able to give you lecture, because I have an official trip to the German island. Okay, so I'm not able to give you lecture. So I just change the time. Okay, the midterm to 2 weeks later. Okay, so next week I will give you the lecture here. Okay, for this course. Okay, so that means I defer the midterm 1 week later. Okay, is it clear? Okay, any problem about this? No. Okay, no, you don't have to come to the class for this course. So similarly, I will give you the online test. Okay, so let me specify this. So next week, okay, is 18. We will have lecture here, okay, next week. But 2 weeks later, 25th, okay, April 25th, you will have your midterm for this course online. You don't have to come to the classroom. Okay, so you can do it in your library, in your dorm, okay, in your location anywhere, okay, you can complete your midterm. Okay. Any other questions? Is it clear? Okay. Because the reason I just mentioned, because I have an official trip to Jinmen Island, okay, on 25th. So I will not be able to come to the class. So that's the reason. Okay, just tell you that. Okay, so that's about the schedule. Okay, so now we're moving to the confusion matrix. This is very common tool to evaluate the accuracy of classification. Okay, so confusion matrix is simply a matrix that compares actual categorical levels to the predicted categorical levels. Okay, so when we predict the right level, we refer to this as a true positive. However, if we predict the level event that did not happen, this is called a false positive. Okay, so true positive, okay, true positive is, that means we are making the correct prediction. Okay, but false positive, that means we are predicting a positive value. However, the real value is negative. So we call this as a false positive. Okay, so alternatively, we also have a false negative. Okay, false negative. That means we predict that we predict that event will not happen, but it does happen. So it is called a false negative. So we like to calculate these numbers. So you can use this. You can check this plot, okay, to see we have false positive, true positive, and true negative, which is on the diagonal part. That means we are making a correct prediction. Okay, we are making correct prediction, but on the off diagonal part, we see false negative and false positive. Okay, but this is just for your reference. Okay, we are not so interested in this metrics. Okay, but we just like to focus on the accuracy. Okay, accuracy. This is the first one. And of course, sometimes we will calculate the sensitivity and the specificity. Okay, so specificity is how accurately does the classifier classify the actual non-events. Okay, so in this case, you can see we have true negative. Okay, true negative is 50. And divided by the true negative plus false positive. Okay, so this is about the specificity. Okay, so it seems a little bit complicated at the first sight, but it will take you some time to understand what exactly these measures are about. Okay, so now I won't spend time describing the details here. What we really care is that, okay, what kind of numbers, okay, we really care, okay, to evaluate our model. Okay, but before we start, you can I just provide some reference down here at the slides here. Okay, you can check out these slides, because these slides, okay, these Okay, sorry, this link, okay, there are two links here. These links are very useful, and these links provide a very detailed description about the confusion matrix. Okay, so now we don't want to spend time describing this. I just like you to study by yourself. But in terms of the codings, okay, it's also not very difficult because we also have a function called confusion matrix. Okay, confusion matrix. For example, like we can now we are using the model 3, okay, and based on the trained data and generate our predicted values. Okay, so you can see the codings here. We have a predicted class here. Okay, so all we have to do is just to provide the predicted class, okay, the predicted output, and the reference is set to be yes. Okay, so in this case, if we set the reference to be yes, okay, then you will see the output. We have a reference on columns, okay, and the prediction on rows. Okay, so this may be a little bit different from the box chart, okay, from the box chart here, okay, because you can see the predicted events. Predicted events are specified as columns, okay, and actual events are specified rows. But here we just change the order a little bit, okay, just transpose the box so you can see here. Okay, so but never mind, this is just for your reference. That shows the model confusion matrix. Okay, the model is based on the model 3. Okay, so in viewing by checking the output of the confusion matrix, we can find there's a number called okay, we have accuracy here. Okay, accuracy is 0.9007. okay, so that refers to the accuracy here. Okay, accuracy here. Okay, so that is the that means how often is the classifier correct. Okay, how often is the classifier correct? So you can see we have a true positive plus true negative. Okay, and divided by the total of samples. So in this case, we got the 0.91. Okay, so this is the accuracy here. Okay. And another information is the no information rate. Okay, no information rate, that means the ratio of non-attrition versus attrition in our training data. So you can calculate the rate to be 83.9. So the let me see. Just a minute. Okay, I'm gonna check the reference link here. Okay, so this reference is created by the Korean. Okay, but never mind. Let's just focus on the some explanation of the confusion matrix here. Okay. So you can see there's a detailed explanation about this, okay? Okay. So what is no information rate here? That means the accuracy that could be obtained by always predicting the majority classes, okay? So in this case, we have the okay, so you can see the majority cases in this sample is no, right? Okay, so if we are always predicting no, then we will get accurate rate, which is 83.95%. Okay, so that would be okay, 83.95%. So you can try to calculate this ratio, okay, because the most of the data in our reference are no, okay. So based on this, if we are just predicting for every sample we collected from the sample, we are just predicting no, okay, that means we are always right, okay, by predicting no, then the ratio will be 83.95. So that is the no information ratio. That means this does not provide any additional information, okay, because we are always standing on the majority side, okay. So this is about the no information ratio. Okay, so next matrix is about the ROC curve. So this will be more important because now we have 3 models. We need to verify or compare if any of the models, if any of the model is performing better than other models. Okay, so we call this ROC. Okay, so ROC curve helps us to visualize the trade-off between the sensitivity rate and the specificity. Okay, so a better or perfect classifier would have ROC curve that passes through the top left corner of the plot. So if you check the plot here, okay, we have okay, here x-axis is a false positive rate and the y-axis is true positive rate. Okay, so that means we like to see the model showing a curve closer to the top left corner. Okay, so if the curve is more closer, okay, to the top left corner, that means this model is better. Okay, so I just recognize this chart, okay, by checking these features. Okay, maybe I don't really care so much about the ROC curve, how we get ROC curve, but what I'd like to check is the chart. Okay, if we can generate models having a ROC curve closer to the top left corner, that means this model is better. So in this chart, we can see we are comparing 2 models here, CV model 1 and CV model 3. Okay, the CV model 3 is in blue curve, so you can see the model is performing better than CV model 1. Okay. To generate the ROC curve, there are so many packages. Maybe there are 3 or 4 packages to help you to generate the curve. So here is just an example. Okay, we have ROCR. This is a library called RCR. So you can just copy the codings here, okay, to generate the plots down below. Okay, just to generate the curves here, okay, just like this one. Or you can just reference the link I provide. So let's check the link here. Okay, so if you check this link, you can see down here there are also ROC curve codings. So you can generate the coding. So in this case, the author is using another library called PROC. Okay, so that means that P must be plot. Okay, plot of RC. So that is PRC package. So down below here, you can see the author can generate the RC curve for the logistic regression model. Okay, because we have so many models, so that we need to compare their performance here. Okay, so down here you can see this is RC curve. Okay. Okay, so this is another link to generate the RC curve. I remember the author is using different packages, okay, to generate the RC curve. Let's wait for a while. Oh, it's too slow here, so let's just forget about it. Okay, but you can check the website, okay, by yourself. I remember the author is using a different package to generate the RC curve. Okay, so this is about the RC curve. I think that this will be more important because in the future we have so many models to check. So here is a practice for you to plot the RC curve for the default model. So for example, like based on the model of table 4.1, 4.2, and 4.3, we need to measure we all evaluate how these models are performing in the prediction of the default. So you can check the table 4. Okay, you can check the textbook 4.1, table 4.1. We are using one variable to explain the default probabilities, which is balance. Okay, table 4.1. We also have a table 4.2. We are using student status to explain the default probabilities. And 4.3, we are using the balance, income, and the student status to explain the default probabilities. Okay, so based on these models, you are required to generate the RC curve for these, for these 3 models. Okay. Okay, so but this will be your practice, okay, by yourself. But because we don't have so much time to for you to do the practice, so we will move on to the other sections of the book. Okay, And in the following slides, okay, I also provide some additional materials, but these slides may seem irrelevant right now at this stage, so I'm gonna skip that. Okay, so I will go to the second slide, second PPT file. Okay, that is the I think that should be this one. Okay, this one. Okay, so this is the one we need to check. Okay, previous logistic regression, we only have two results in our response variable. Okay, so I have discussed this model last week, but last time. But this will be more complicated models. We call this as a multinomial logistic regression. Okay, multinomial logistic regression is different from the multiple logistic regression. Okay, because now we have more than two results in our response variables. So for example, like this one, if we have y equals to 0 and 1, but now we have y equals to 1, 2, and 3. Okay, so one is stroke. The second is, this is about the patient data. If the stroke patient or drug overdose patient or the epileptic seizure patient, so we have 1, 2, and 3. So basically, this is the model we like to predict if this patient is seizure, is a stroke or drug overdose or epileptic seizure, conditional on their patient features. For example, like their age, okay, like their blood pressure, like their health conditions, etc. Okay, we like to predict if this patient is belong to the 1, 2, or 3. Okay, so this is called the multinomial logistic regression. But this will be more complicated. The thing is that if we want to interpret this, okay, that will be more difficult and more complicated. Okay, so in handling this kind of model, we need to be very careful. But in the beginning, okay, last time we just mentioned some statistical equations here. Okay, we have multinomial logistic regression here. So in this case, we have do some manipulations that mathematically. Okay. So what we are trying to do is, okay, we just assuming that we have a K response. Okay, we have a K response, but our explanatory or predictors are P. Okay, so you can see here in our predictors here, we have okay. So let's check out this equation. So in this case, we have x1, x2 until xp. Okay, so p is the predictor, and but for y, we have k responses, k types of response. Okay, k equals 1 through k minus 1, but finally we will consider we will treat this all the same. Okay, but now for now we only have k equals to 1 until k minus 1, because we wanna we're gonna select one k, capital K, as a base model. Okay, base model, and we like to compare if the small k compared with big K. Okay, what's the probability, or what's the difference of the probability? Okay, predicted probability this model can generate. So similarly to the previous 0 and 1 case, now we have k different types of response. Okay, but even in this case, we will have we still need to compare the probability. Okay, the probability difference, or we call this is a log odds. Okay, but this time the log odds is not 0 and 1, but we need to specify the base model, which is big K, and we need to select the small k. Okay, that is to be evaluated. Okay, so maybe we can move step further here. Okay, so for example, in this case we have an emergency room visit into stroke, drug overdose, epileptic seizure. Okay, so in this case, if we set epileptic seizure to the baseline, we can interpret beta as the log odds of stroke versus epileptic seizure. Okay, so just keep this in your mind. We always have to set a response, okay, Y response value to be the baseline. Then we can compare the log odds, okay, based on the estimated regression. Okay, so this is about the multinomial or logistic regression. Okay, so if you want to interpret the results, then maybe you can say that one unit increase in XJ associated with beta stroke increase in log odds of stroke over epileptic seizure. So now we are comparing these two models only. Okay, so this is a better way to interpret the results. Okay, so this is just for your reference. And okay, this is about the modeling. Then if we want to do some estimation, but because the estimation is more complicated, so I will give you just concepts, okay, just overall concepts about the estimation. Basically, what we are doing is we try to find the maximum likelihood, okay, and this will involve the following. That means we will treat, so here we are using the softmax coding. So softmax coding, okay, rather than selecting a baseline class, it treats all K classes symmetrically. Okay, and the purpose is that this can make our optimization easier, a process easier. So in this case, what we got is log odds ratio between K and the K plant classes. Okay, so we'll get the following equation, and based on this equation, then we can use the optimization process. Okay, so that's just before we start, then we can just make some changes about model. Okay, so here are just some reasons why we need generating models for classification. So that means why we need generating general models for classification, because there are several reasons. Okay, there are three reasons. The first reason is when there's substantial separation between the two classes. Okay, so this is the first reason. The second reason is if the distribution of the predictor X is approximately normal in each of the classes and the sample size is small. Okay. Then the approaches here will be more accurate than logistic regression. And the third reason is the methods here can be naturally extended to the case of more than 2 response classes. Okay. So in this case, then we need to go to the Bayes theorem a little bit further. Okay, because now what we are doing is that, okay, now we are using the Bayes theorem. Okay. So, you know, because originally what we are doing is this, we call this as a posterior probability. That means the probability of y equals small k conditional on x. Okay, so this is posterior probability. Then we can reformulate the posterior probability to be the prior probability in this formula. So we call this as the Bayes formula. Okay, so let's go back to here. Maybe this will be more clear to you. You can see here on the left hand side here, let's look at the lower equation here. So this is the posterior probability. Okay, we like to estimate the probability of y conditional on x. Okay, and this will be equal to this on the right hand side here. Okay, so based on the right hand side equation, we can reformulate this, okay, to be the equation of 4.15. Okay, so you can see this is 4.15. So pi k, okay, here refers to p probability of y equals to k. So this can be easily obtained. Okay, but on the other hand, we have a more problem. What we have problem is this part. Okay, this is called f k of x. Okay, f k of x, that means probability of x conditional on y equals to k. Okay, so this is prior probability. Okay, so the problem is fk of x, okay, that denotes the density of function of x for an observation coming from the kth class. So in this example, that is the probability of being over 60, given that you have had a stroke. Okay, so suppose you have a stroke here, okay, and we like to estimate your age, okay, over 60. Okay, so this is called a prior probability, but usually this probability is difficult to estimate. Okay, so we're gonna take a different approach to handle this fk of x. Okay, so now this formula, okay, this formula may seem very difficult to estimate, but now we try to reformulate this formula, okay, to be this on the right hand side, and based on the formula on the right hand side, we can see the most difficult part is this probability density. Okay, so this will be the most difficult part to solve. Okay, so now let's dig one step further. Okay, so now, okay, we have a posterior probability. Posterior probability, we denote this as pk of x. Okay, pk of x. And then to compute the posterior probability, we have to estimate the pi k and fk. Okay, so what about the pi k here? Okay, so based on this, we can find a way to estimate fk of x, then we can plug into equation 4.15 to approximate the Bayes classifier. Okay, so how can we do that? Okay, so here comes the linear discriminant analysis. Okay, so now we are introducing an approach called Bayes classifier. Okay, so Bayes classifier, that means we try to assign observation to the class. Okay, that makes the pk of x the largest. Okay, so this is different from the Bayes theorem. This is more about the estimation approach. Okay, so what we are doing here is that we're assuming that fk of x is normal Gaussian. Okay, in the one-dimensional setting, the normal density will take the form. Okay, will take the form. So this is referring to the normal distribution, standard normal distribution, whatever, because we are assuming that the normal distribution for our observations here. Okay, so this is the easiest part. So fk of x is taking a normal distribution, and then you can see the mu k and sigma k are the mean and the variance parameters for the kth class. Okay, so based on this, we call this as a Bayes classifier. Okay, different from the Bayes theorem. Okay, and based on this, then we can plug in to the equation, plug in 4.16. Okay, 4.16. But now you can see, okay, so this is 4.16, and plug in this into the 4.15, okay, and you will get the 4.70. Okay, so this is the posterior probability. Okay, then we can transform the posterior probability into this formula. Okay, and the thing is that if we only have one predictor, okay, which means we only have one x, that means we only have, that means we can assume that the standard deviation, okay, standard deviation is equal to sigma instead of sigma k. Okay, now you can see we are applying the same sigma. Okay, we don't have to worry about the different sigma for different k's. Okay, because now we're assuming that they are coming from the same distribution here. So based on this, then we can take the log of 4.17. Okay, 4.17, we are taking the logarithm, okay, and we simplify the result, and we will get these results here. Okay, so we'll get the delta k, okay, and this is called the formula 4.18. Okay, so what we are doing here is, okay, we try to maximize. Okay, maybe you can treat this as a probability or something, anything like the probability. What we are doing here is we are assigning the observation to this equation to maximize the probability, to maximize this value. Okay, so this equation is also called, okay, now we call this equation to be the discriminant function, okay, which is a linear function of x. Okay, so this may seem a little bit complicated, but mathematically, okay, it's more complicated. But conceptually, you need to, what you need to focus is that, okay, now from the beginning, okay, we have a posterior probability. Okay, posterior probability can be reformulated to a ratio, okay, on the top, okay, on the bottom is probability of x. On the top, we have a pi k multiplied by fk of x. Okay, so this is called the prior probability. Okay, so prior probability, to estimate the prior probability, we just make assumption of that. Okay, assuming that this prior probability is following a normal distribution, the density of normal distribution, and then we can reformulate the result in this way, and finally we'll get the this output. Okay, so for instance, if we only have two classes, okay, two classes, that means yes or no, 1 or 0, and assuming that pi 1 equals to pi 2, okay, and then why we have to assume pi 1 equals to pi 2, because that can maximize the probability here. Okay, so we can simplify the results, and then finally we'll get this value. Okay, so this value is called a Bayes decision boundary. Okay. Okay, so this is called delta 1 equals delta 1 of x equals delta 2 of x. So for the delta k, you can treat this as a, if this delta k is bigger, okay, then we can classify the output to be for example, this is delta 1, okay, if k is equals to 1, then we can classify this output to be to belong to the classes 1, okay, otherwise it belong to classes 2. Okay, on this chart you can see we have a two. For this one, we only have one predictor. Then you can see that the only difference is that, okay, we have a Bayes decision boundary. We have 20 observations were drawn from each of the two classes. Okay, so we can calculate the Bayes decision boundary. Okay, you can see the Bayes decision boundary is shown on the as a dashed vertical line. The solid vertical line represents the LDA decision boundary. So these two are very close to each other. Okay, so this is a linear discriminant analysis. So based on this linear discriminant analysis, we can we are discussing the Bayes classifier, but now we are using the linear discriminant, okay, to approximate the Bayes classifier. Okay, so put it another way, the linear discriminant analysis can approximate the Bayes classifier, okay, using the following formula. Okay, so summary, the LDA classifier results from assuming that observation within each class come from a normal distribution with a class-specific mean and a common variance, sigma square, and plug in this estimate out so that we can approximate the Bayes classifier. So that's the advantage of the linear discriminant analysis can do for us. Okay. So this is just a very short introduction of linear discriminant analysis. And in the following, we will have some examples. Okay, let's take a break. We'll come back later.